right. MCT4C, day 40, part B. Our second half of day 40 is the first chunk of 5.3, which is comparing polynomial functions. And essentially, we've just got a bunch of stuff to learn about polynomial functions, and we're doing it little bits and pieces at a time. This 3-minute review is about some algebra. All right, so the algebra here, some function notation. We practiced this earlier in the year. The idea of when I have a function f at x equals 2x squared minus 4x, whatever goes there, I fill the hole with whatever's in there, and it's 3 this time. That I can put into my calculator in one step, and I get 2 times 9 minus 12, 18 minus 12 is 6. But not always is it numbers. I can do stuff that that just adjusts the formula. So here, this is 4 times whatever f at x is. Well, f at x is equal to this. So this is 4 times that function, right? 4 times that function, that's 8x squared minus 16x. And since it's not in with the x, back when we were talking about transformations, we could think of this as a vertical stretch too, right? And that's what it did, right? It stretched those numbers. This one, on the other hand, I can see when it's a minus in with the x, that's a horizontal flip, right? If we were talking about transformations of trig functions or whatever, this is a horizontal flip. It's flipped in the direction of x. But that's not what we were asked to. We were asked to calculate what this is algebraically. So I'm just going to, in the function, take out the x, it leaves a hole, and I'm going to fill it with what's there. It's a minus x. It's a minus x. Now I've got some algebra to do. Negative x squared means negative x times minus x, which is negative times negative positive x squared. So this is 2x squared. Negative 4 times negative x is positive 4x. That's all well and good. Here, negative 4x, and that's a vertical flip. The transformation would be a vertical flip, but here, it's just the negative of whatever f at x is, and f at x was that function. Okay. Is that right? Yep, looks good. Question number 2 from the 3-minute review. Use your expressions from number 1, and I'm asked to graph them all. Sketch what you see here. Okay. I'll warm up the old graphing calculator. What do we got? It's all that differences stuff from earlier in the class. What do we got? We got f at x is 2x squared minus 4x. F at negative x ended up being, and I'm going to make the first one thicker just so I can compare to it. Make that first one thicker. You don't have to do that, of course. You've done this yourself. You're just watching me take it up. I hope. That's the plan anyway. And then thirdly, negative 2x squared plus 4x. And it says to use zoom 4. That's the first one. There's the second one. There's the third one. Okay, so I'm going to copy those, just roughly. First one, that's f at x. Second one was kind of over here, going this way. That was f at minus x, and the third one was upside down. Well, that kind of makes sense. How does the graph of f at minus x, the red one, compare to f at x? Well, just like we thought, it's a horizontal flip. It's a flip over the y-axis. It's a flip this way. This part gets flipped to here. This part gets flipped to here. horizontal flip. And that's over the y-axis. And we kind of knew that because that's what that transformation was. How does the graph of the red one compare to the graph of the green one? Well, the purple one to green one is just a flip this way, and red one to purple one was a flip this way. So it looks like they've been flipped twice. It's a double flip. It kind of looks like. And another way to think of this is that it's been, we could think of it as having been rotated around that point, right? If I were to take this green one and just sort of grab it and rotate it around, it would be the red one. And I wonder if I can actually do that. Rotate it around. I'm not rotating it around the correct point, right? It's rotating around this point, but pretend it was rotating around the origin. Yeah, it would be. That would be a rotation. This is what's called point symmetry. Okay, we could think of it as a double flip, a flip this way and a flip this way, but it's also called point symmetry. Okay, so however you would like to describe that, call it a flip through the origin, or a flip over both axes, however you think of it. This is actually called point symmetry. And these two things, these two relationships, are what we're talking about in this short lesson. 5.3, investigate using technology the characteristics of polynomial functions. The idea today is this idea of even and odd functions. So we've got a function here, and it's polynomial functions that have the y-axis as a line of symmetry have a special property. Okay, you see how in this graph, this is the graph y equals 2x squared minus 3, that the y-axis is a line of symmetry. If I were to reflect it, I'd get the same graph back. So geometrically, the reflection of the y-axis gives the same graph. So when I flip this line becomes over here, this point would be over here. It's symmetric. Algebraically, what do we say? Say, well, if we had the graph, I'd get the same thing in if I put a positive value as a negative. And this also makes sense because we know the minus with the x meant a horizontal flip. So the horizontal flip doesn't change the graph. In the 3-minute review, it did, but in this one, I'd get the same graph back. If I were to graph this one, I'd get a graph right on top of it. Watch this. And watch. Okay, so we know that f at x was 2x squared minus 3. But watch this. If I did the same trick that I was asked to pull in the 3-minute review and graph and calculate f at minus x, take out the x and put in minus x. And I'm going to tidy that up so you can actually see the minus. Minus x, well, what would I have? Well, negative x squared is 2x squared. And then the minus 3 tags along. And now look, I've got f at x equal to f at minus x. That means this happened, and this is called an even function. These functions are called even functions. Notice, don't confuse this with an even degree function. Even though this one happens to be even degree, not all even degree functions are even functions, as we saw in the 3-minute review, right? This one was 2x squared plus 2x squared minus 4x, this purple one, but when we flipped it in the y-axis, it wasn't the same graph. Even functions, you have to have the same graph when you flip it in the y-axis. So if this is an even function, is there odd functions? There certainly is. Polynomial functions that appear to be symmetric on a rotation around the origin. So notice if I took that chunk and sort of rotated it around up there, this is also called point symmetry. It's a reflection over both x and y axis. This is called an odd function. So notice that if I flip this function in the x-axis first, it would kind of go, this would kind of go like this then. And then I flip it this way, I'd get back to my original graph. So you can think of it as those three different ways. We could think of it as a rotation. We could think of it as a double flip, the double flip symmetry. Or I could think of it as a point symmetry, where some point on the graph, if I go through the origin the same distance, I'm going to be at the sort of same spot in the graph. All three of these things mean the same. Algebraically, we write it as this, okay? We write it as f at minus x. Minus x, remember, was a horizontal flip, would give me the same graph as if I flipped it vertically. And notice that's what we were investigating in the 3-minute review, and it didn't quite work. But if this red graph and this green graph would have been the same graph, then the original function would have been an odd function. So this one I'm saying is odd. We've got f at x equals x cubed minus 4x. And watch, this is going to be true. So I take out the x, I put in a minus x, and then I'm going to do some algebra. Well, negative x to the exponent 3 is negative x times negative x times negative x is negative x cubed. Negative 4 times negative x is positive 4x. And notice that that's not the same as the original. So I know this function's not even. But for it to be odd, I have to investigate, well, what happens when I take f at x and multiply by negative 1. Here's the f at x. That's the f at x expression right there. That's the same as that. Well, how do I get this calculation? I just multiply through by minus 1 into the brackets. A little bit of algebra didn't hurt us. And now notice, what do I got? This graph, this expression, and this expression are the same expression. Therefore, f at minus x is equal to negative f at x. And this means f is an odd function. Okay? Not an odd degree function, but an odd function. This is the picture. And in the homework, you'll be investigating this. Notice a function doesn't have to be either even or odd. There's lots of functions that aren't even because this property doesn't hold, so they're not even. And this property doesn't hold, so they're not odd. And so it's possible for lots of functions to be neither. All right, I'm going to go through my only example here. I think this is my only example, yeah. And then that's going to be it. Determine if each function is even, odd, or neither. Check your work using graphing technology. Okay, so if it's even, what I do is I start with the original function, and I want to see if it's the same thing if I put in minus x in its place. Okay, well, I got a little bit of algebra work to do. Negative x cubed is negative x to the exponent 3 on the outside. 4 times 9 minus x is minus 4x. I'm going to clean this up a little bit. The number parts should go all at the front. And notice, is f at x equal to f at minus x? Is this expression here the same as the one we started with? Absolutely not. So we can say f is not even. But is it odd? Well, let's check it out. The next expression I want to check out is negative f at x. Negative f at x is that expression. A little bit of algebra. And what do I got? This expression and this expression are the same. So then I can say, therefore, f at minus x equals negative f at x. Therefore, f is odd. And I should, when I graph those two, I'm going to graph the original. It should look like, and I got to get rid of all that other crud, clear all this other crud off. It should look like that double flip symmetry, or it should look like a rotation, or however you like to think of it. 2x to the exponent 3 plus 4x, and I press graph. Oh, it's pretty thin, but does it look like it's a rotation or a double flip? Absolutely it does. Okay, what about this one? First, let's check out f at minus x. Take out the x, dump in minus x, and see if it's the same expression. 4 times minus x is minus 4x. Are these two things the same? No, there's a minus in the wrong spot. So they're not the same. F at x is not equal to f at minus x. If it was, it would be even, but it's not. So it's not even. Well, now let's check out the last expression. Let's see if this bad boy's odd. Whoops. Here, taking the f at x expression, which is that expression, and just multiplying by negative 1 out front. And what do I got? I got negative x squared minus 4x minus 5. Well, there's the minus, but are these two expressions equal? F at minus x, which is this one, and this one. They're not equal. So f at x is not odd. F at minus x is not equal to negative f at x. F is not odd. It's neither. So when I graph it, I shouldn't see a flip over the y-axis symmetry, and I shouldn't see a rotational symmetry. Let me just check that one out. So what was the original function? It was x to the exponent 2 plus 4x plus 5. I press graph. No, if I flipped it over this axis, it would be down there. If I rotated it around the origin, it would be down here somewhere. This has no symmetry, this graph. It's neither even nor odd. Okay, that's it. Good luck with the homework. You get to play with the calculator still, so have fun with that.